before the holidays, and test 2 is going to be, this is the syllabus. Test 2 is going to be about chapter 3. Okay, the suggested date is 17 of May. So from now, it's almost 12 days. And we finished chapter 3. We finished all the tutorial of chapter 3. So we are ready for the test. Okay, and you have you can study. You have 2 or 12 or 10 days, 12 days to study for the test. Okay, so chapter 4 is about vibration or transient vibration. This is the familiar name. The transient vibration was, we have seen this in chapter 3, that the total solution, if there is a force vibration, it consists of two parts. The first part, which is the complementary solution, and the second part was the steady state or the particular solution. The complementary solution, we called it transient solution, and the reason is that it will decay with time and it will vanish, and then you will have only the steady state, the particular solution. Here it is a transient. The reason it is called a transient, it is depend on the force. There will be a force applied here, and that force will not create the steady state part or the particular solution. Okay, so it is the force is applied as over a short time, let's say, or over a period of time, and then it will be removed. It's like we have a pulse. Okay, pulse, it means you put a force and then you remove it. So that will create a response for the system, and that response will be only exciting the transient part, the homogeneous part only. And then the particular solution, there is it is not excited, and the vibration will decay with time if there is damping, and then it becomes like free vibration. Okay, so this introduction says, when a dynamical system is excited by a suddenly applied non-periodic excitation, f of t, the response to such excitation is called the transient response, since steady-state oscillations are generally not produced because this force is applied over a given time or a period of time. Such oscillations take place at the natural frequencies of the system, with the amplitude varying in a manner dependent on the type of the excitation. So we will start with impulse excitation, which is, and then we will generalize the excitation to pulses. So what is the transient here is the response due to a force applied over a period of time, but not periodic. You know, periodic is the sine wave, cosine wave, or harmonic forces. Also, in general, it is not periodic force. That means it is not existing all the time, and it is not repeating itself in an equal interval of time. This is applied over certain period of time, and then it is removed. The characteristics of the resulting excitation here is that the vibration will take place under the natural frequency. So if the system is undamped, the vibration will be under will take place under the omega n for single degree of freedom system. And if this is damped, it will take place under the frequency omega d for under damped. Okay, and there might be no oscillations for overdamped or critically damped. Okay, this is also a good way to find the natural frequency of unknown system with unknown characteristics or unknown natural frequency. So you can apply measurements and give forces that causes excite the transient part of the system, and then you can determine whether you have you can determine the natural frequency. Okay, in some cases, in machines, for examples, or even structures, when vibration is very large in magnitude or in amplitude, then you might think that the machine or the structure is under resonance. You know, at resonance, you have the vibration is very high. And if you have no prior information about the natural frequency of the system or structure, then you can apply such technique that you apply an non-periodic force and measure the resulting vibration and determine the natural frequency. Because with non-periodic excitation, you are producing the transient part, which is the free vibration part of the response. And we know that it takes place under the natural frequency, and you can determine the natural frequency. So and then you compare the natural frequency you obtain by measurements with the excitation frequency at which we have a large vibration. Okay, so this is used, and maybe one of the examples is about this. Okay, so we'll start with impulse excitation. This is by definition, first of all, you know, impulse is the time integral of the force, which means integration of f dt. Integrate this over time, and here it is given as f hat. That is the definition or the designation of the impulse, and the unit of the impulse is Newton second. Okay, because force times time. Okay, but this is in general, you know, we have did this in dynamics, and we use the principle of impulse and momentum in dynamics for particles, maybe chapter 3, I think. Okay, and we use we gave a name different than so we give impulse IMP from 1 to 2. So the impulse, it means integrating from T1 to T2. If it is over time. Now, if you have a force that is very large in magnitude and applied in very short time, then you create impulsive force. Okay, the impulsive force is in magnitude, it is very large compared with the other forces involved in the system. Okay, an example of this in dynamics we gave is the baseball, okay, and the bat. Okay, when the bat hit the ball, the force exerted by the bat is very large compared with the weight. So that can be neglected. You know, you can neglect this as 0 as compared with the applied force. Okay, so when the system has a very large force and applied in very short time, okay, because with the bat and the baseball or the ball, it will take fraction of second to be in contact, but the force is high enough to change direction of the motion of the ball and as well as the velocity. Okay, and it is called impulsive force. We can represent the force over with the axis of time. Let's say this is applied at time equal to eta. I will change this character to eta, and duration is epsilon. Okay, so it is applied at a time t equal to eta. It can be applied at t equal to 0 as well. Okay, and at t equal to 0, it means it is applied here. So eta equal to 0. Okay, the magnitude or the duration is very short, epsilon, which goes to 0. And the magnitude of the force is called infinite. And f hat is known, is finite. So the magnitude of the force is given as f hat over epsilon, which is very high. Epsilon goes to 0. Okay, so as epsilon approaches 0, such forces tend to become infinity. However, the impulse defined by its time integral is f hat, which is considered to be finite. So this value is finite, and it is measurable. You know, it is given by Newton second. But if the force itself is very large, it's not given. Okay, it is something very large. That is an ideal case. Okay, that you assume that the force goes to infinity and that the duration goes to 0. So imagine that the forces goes to infinity and applied in 0 time, and that becomes something ideal, but this will help us to develop for a more practical and realistic cases. So when you apply this on a spring mass system subjected to impulse, so there is spring with a stiffness K and a damper C, and you have a mass M, then this is a force F of t applied here, but this is the impulse force, which means it is applied over, let's say, 0 time, at 0 time, over very short time, at t equal to 0 and over a short period. Okay, so what you can do here, you apply the Newton's second law. Sum of forces equal to mx double dot. Okay, so let's say that this system is at rest. Which has 0 initial displacement and 0 initial velocity. Now the forces here is only F, which is the impulsive force, and M times x double dot. We will define this by its definition, which is dv by dt. Right, this is the acceleration, and then you multiply by dt both sides. You get F times dt equal to m dv. When you integrate both sides from T1 to T2, and this will be m is constant, and this is a mass solid, and then it will be from V1 to V2. Now here the intervals T1 and T2 are 2 different instants of time. T1 or V1, it is the state before applying the impulse, just before. Okay, so state 1 or instant 1 is just before the impulse is applied. And instant 2 is just after the impulse is applied. Okay, so if the system is initially at rest, it means its initial velocity is 0. Okay, so this will give us the left-hand side is f hat. So f hat equal to m v2 minus v1, and for system initially at rest, v1 is 0 because this is the velocity before. Okay, v1 is the velocity before the impulse is applied. And v2 is not 0. As you can see, v2 becomes equal to f hat over m. And this velocity is, v2 is the velocity just after the impulse. Okay, just after the impulse is applied. Okay, and this, as we said, the impulse is applied over a period of time approaches 0. So this means v2 becomes the initial velocity to the system, of the system, or of the mass. Okay, just after after the impulse. And then you can work on the system or on the solution of the system with initial velocity now is given as f hat over m, with initial displacement is 0. So the impulse is changing. It is suddenly changing the initial condition of the system from rest to v2 equal f hat over m without an appreciable initial displacement. So the new initial conditions become, here we said that the system is initially at rest. It means that x at 0 is 0. X dot at 0 is also 0. But after the impulse is applied, the initial conditions become x at 0 stay as it is, 0. However, x dot at 0 is equal to f hat over m. And then it becomes an initial value. It comes, you have the initial conditions without force, because after the impulse, the system is oscillating without an applied force from on the system. So it means it is under free vibration. Okay, so this is this paragraph says, because if dt equal to mdv, the impulse f hat acting on the mass will result in a sudden change in its velocity equal to f hat over m without an appreciable change in its displacement. Under free vibration, we found that the undamped spring mass system with initial conditions, x at 0 and x dot at 0, behave according to the equation. You can check chapter 2. Okay, this was the equation of the response for undamped system, that x equal to x dot at 0 divided by omega n sine omega in t plus x at 0 cosine omega in t. With if the system is initially at rest and excited by impulse f hat, then you can write x equal to f hat over m omega n, because x at 0 becomes 0, and we have only x dot 0 over omega n, and x dot 0 at 0 is f hat over m. Okay, so we have x becomes x dot at 0 divided by omega n sine omega n t, and this will lead to replacing x dot with f hat over m. We will have x equal to f hat over m omega n sine omega n t. Okay, and then we can write also that x equal to f hat times h of t, where h of t is 1 over m omega n sine omega n t, is the response due to a unit impulse. So if f hat equal to 1, then what you get? You get x equal to 1 over m omega n sine omega n t, which is, this is called h of t. Okay, which is the response to a unit impulse. If you have underdamped case, when damping present, and this is specifically for zeta less than 1, from chapter 2 as well, that the response to initial conditions of underdamped is given by x dot at 0 e to power minus zeta omega n t over omega n square root of 1 minus zeta squared sine square root of 1 minus zeta square omega n t plus x0 cosine omega square root of 1 minus zeta square omega n t, but that one is omitted here because x at 0 is 0. Okay, again, you can write, if this is an impulse, then you can change the initial velocity to f hat over m. Okay, because the impulse is applied and removed before the system starts to oscillate, and that will give change in the initial condition, which is the initial velocity. So it does not depend on the system. Okay, the system is excited by impulse, and then it will respond according to the initial the change in the initial velocity. Okay, so here is for underdamped case, when x dot 0 equal f hat over m, is x becomes f hat over m omega n square root of 1 minus zeta square e to power minus zeta omega n t sine square root of 1 minus zeta square omega n t, which is also can be written as f hat times h of t, but h of t here is not same as the one above. Okay, h of t is 1 over m omega n square root of 1 minus zeta squared e to power minus zeta omega n t sine square root of 1 minus zeta squared omega n t. When you put f hat equal to 1, that is the response due to unit impulse of underdamped system. And we can make this also shorter when we use the definition of omega d. So this will be 1 over m omega d e to power minus zeta omega n t. Let me take this down. Okay, e to the power minus zeta omega nt sine omega d t. And for underdamped, omega d is equal to omega n square root of 1 minus zeta squared. Okay, here is an example in the vibration testing of a structure. Okay, so why there is testing of the structure is usually by suspecting that the vibration goes under resonance, or you want to test or find out the characteristic of the structure. One way of or the characteristic that to be found are either omega n or the damping ratio zeta. So you can apply an impact hammer, or this is called impact testing. We use a hammer. This hammer is not a normal one. This has a load cell which can measure the impact and the force, and calculate for you the impulse itself. Okay, so in the vibration testing of a structure, an impact hammer with a load cell to measure the impact is used to cause the excitation as shown. So the source of excitation is impulse here, used by produced by the hammer by impacting. And impacting will take just it's like hitting the structure with very short time. Assuming the structure here is as shown in the diagram, is made of columns like cantilever beams, but it is given as k over 2, so we don't have to calculate the value of k because no other parameters are given. So it is the cantilever beam or columns will act like springs of stiffness k over 2, and supporting the mass m. The value of m is 5 kilogram. The value of k is 2000 Newton per meter. The value of c, assuming that the columns will have damping, equal to 10 Newton second per meter. And the impulse as produced or calculated, measured by the load cell, is 20 Newton second. This is F hat. Find the response of the system. The response, which means to find x as function of time after the impact. Okay, from the system we have omega n square root of k over m. You can take a model of this. And then you have the impulse, f of t. Okay, so it is a spring mass damper system. Omega n square root of k over m, square root of 2000 over 5 becomes 20 radian per second. Zeta is c over cc. C over 2 square root of km becomes 10 over 2 square root of 2000 times 5 becomes 0.05, which is underdamped. So this means this is underdamped. And then you can calculate omega d, square root of 1 minus zeta square omega n becomes 19.975 radian per second. Okay, assuming that the impact is given at t equal to 0, as you can see from here. This is 0 here, and this is the impulse at t equal to 0, and this is f underline is f hat. In we used to call it f hat, but this is from another reference. It is used representing the impulse with underline. Okay, so since this is underdamped, then if x equal to f hat e to the power minus zeta omega nt divided by m omega d sine omega dt, and then we just put the values. I don't think we need this. So 20 divided by 5, 19.975, e minus 0.05, 20t sine 19.975t, which becomes 0.2 e to power minus t sine 19.975 t, and this is in meter. Okay. So I think this is the end of this lecture. I will make it short today. Any questions? Okay, next time we will talk about general type of or more realistic excitation, which will be a force applied over period of time, but not periodic. Okay. Yeah, we'll see you next week. Next week, I'm planning also to give you the labs. I don't know, the labs, since most of you are online, I will also talk about the lab, online. And I was hoping that everybody can come, but even though we have no technicians in the available this semester, so I will, talk about the experiment number 1 next week. According to the timetable we have, I think you have on, is it on Tuesday or Thursday at 3? So we'll follow the schedule, the timetable. At 3, I think it is either Tuesday or Thursday. Thursday, right? Thursday. Okay. So we'll take our first experiment on Thursday at 3. All right. Let's see you.
مع السلامة دكتور.